Hello, I'm Owen Greeley, and I'll be talking about Vyvanse in the treatment of ADHD. So, Vyvanse or lisdexamfetamine is a prodrug for D-amphetamine, which is a stimulant, and stimulants have been used as a treatment for ADHD for over 50 years. They work by elevating synaptic catecholamine concentrations, specifically dopamine and norepinephrine, although dopamine holds more importance. It's become increasingly popular due to it being a single isomer instead of racemic mixture of amphetamine, like all other or majority of other stimulants, and that's why it's did very well in 2015, and there is 30,000 kilograms of it produced in 2016. So ADHD, or attention deficit hyperactivity disorder, is caused by decreased dopaminergic function. Specifically, there's three subtypes that can be labeled as ADHD, and they come from two categories. There's hyperactivity and impulsivity, which is not being able to sit still, fidgeting, always needing to do something, and then also risk taking, not really planning ahead. And then there's the inattention, which is having difficulty focusing for extended periods of time, uh, task recall, and for some people it can be a slight annoyance, and for other people it can be debilitating. And when those combined, you have the combined subgroup, and that's generally what people refer to as ADHD. That's the main populace, and there's estimated to be over 51 million globally just from 2015. So there's no definitive test for it. Uh, it's qualitative. It's more so an assessment of how they act and how far along they are, so to speak, in reference to their peers. And it's primarily done by parents and teachers, which is a partial explanation to why the number is so much higher for people under the age of 18. But some other factors that play a large role in it are genetics. You're three times more likely to have it if you have a sibling with it, and boys are twice as likely to, or I should say, be diagnosed with it, not have it, to be diagnosed with it than girls. So it's believed to be caused by functional impairments, specifically with the dopamine and the noradrenaline neurotransmitter systems. In the prefrontal cortex and the striatum, those two systems are directly responsible for a lot of higher level thinking, such as executive function, motivation, more so like long term goals, and then also motor functions. And what's interesting about this is you don't often see pathophysiological issues when you have mental illness, so to speak. But in here, there's actually across the board the same ratio of decreased left prefrontal cortex size in individuals that have been diagnosed with ADHD. So it sounds simple enough. There's insufficient function of dopamine and noradrenaline, then just increase the efflux and function of them, and also eventually cure the disorder instead of just constantly treating it. So Vyvanse is taken in a capsule, uh, swallowed, and even though the capsule gets broken down by the acidic stomach enzymes, they are not strong enough to hydrolyze the peptide bond between them. So they travel to the small intestine where they're partially hydrolyzed by pancreatic enzymes, but for the most part, they're picked up by peptide transporters and they're taken across the GI tract into the bloodstream where they can be further or mainly hydrolyzed. So you see in the top right, this is trypsin with the pancreatic enzymes would have a similar mechanism too. Um, if you remember that from biochem, and then once in the bloodstream, they're actually broken down by catalytic enzymes inside the cytosol red blood cells. So I would have imagined is more so the pancreatic enzymes, but then it's broken down into purely D-amphetamine and lysine. Okay, so it does three things, but it does two major things. The initial first thing that amphetamine does once it reaches its desired target, once it's active and it hits the neuron, is it goes in through a dopamine transporter and it's going to be a competitive inhibitor for that dopamine transporter. It acts as an agonist for this trace amine associated receptor, which we call it TAR1. And this is a G-coupled protein, so it's going to send a cascade messenger signal, and it's going to phosphorylate this dopamine transporter, which was bringing dopamine in and now is getting beaten by the amphetamine. And once phosphorylated, it can either just be kind of removed from the membrane of it and be in the intercellular fluid, or it can act to move dopamine out of the cell. The other important thing it does is it inhibits, in a way, the vesicular monoamine transporter, which is kind of what it sounds like. It brings monoamines in and out of a vesicle. So we have a vesicle here full of dopamine and norepinephrine. It's gonna reverse transport, so it's going to bring the amphetamine in because it has a higher affinity for it, while also pushing the other monoamines out into the intracellular fluid. So there's pretty much, it does two things. It's the release of the monoamines to the intercellular fluid by having VMAT2 run in reverse, and the reuptake prevention by the cascade of signaling to phosphorylate this dopamine transporter. So even though it says it's blocking reuptake, it's not so much the sense we're used to seeing it, where it's something with higher affinity going in there, is actually just kicking it out of the cell. And so that's going to increase the concentrations within the synaptic cleft even more. So D-amphetamine versus L-amphetamine. The top one is D, and it has a shorter half-life because it has a higher affinity for the receptor. Researchers aren't completely sure what about the stereochemistry changes how it interacts, but it's been observed many times that D-amphetamine works better to produce the wanted effects in stimulants, and L-amphetamine, because it has the lower affinity, it's more associated with the negative effects, like on being unable to sleep and appetite suppressant. And there was originally a pure L-amphetamine stimulant in the 60s, and it didn't last very long, last 2 or 3 years. And now the only pure L-amphetamine derivatives are used as cough suppressants and nasal decongestants, although they still do have some desired effect of the alertness on the central nervous system. So the bioavailability in terms of getting into the bloodstream is pretty similar. They both use peptide transporters to get across the GI tract. But where it differs is once it gets into the bloodstream, it needs to break down from being the prodrug, lisdexamfetamine, into the active compound, D-amphetamine. So you see the graph here, you'll see a correlation of once this starts breaking down, this starts appearing, which makes sense because this is being converted into this. But they did three different groups. One that had fasted for 10 hours and then took the medication while still fasting. A group that ate a high fat diet 4 hours before, or up until 4 hours before, and then a group that had also been fasting for 10 hours and continued to fast, but instead of taking it in a capsule, they drank it in water. They just poured it all out into a solution. And you can see there's very minimal difference. The only thing you see here is that for the group that was fed, it lingers in the system a lot longer, and that's just due to if it's a high fat meal, you're going to be using a lot of your pancreatic enzymes to help break that down. Okay, there's two byproducts. Once it's hydrolyzed, you get the amphetamine and you get the lysine. And the one we'll focus on, it can go a bunch of different ways. We'll focus on norepinephrine to 4-hydroxynorepinephrine because low levels of norepinephrine are what cause the issue. So that would be the most helpful. And the reason that is likely to undergo beta oxidation to become norepinephrine from amphetamine is one of the side effects is appetite suppressant, and that plays a role here with L-lysine. It's a ketogenic amine, and there's only a few of those. So in times where blood sugar is low, this can be converted into acetyl-CoA or ketone bodies through beta oxidation, which can then be an energy source for the body. And if it's likely that this is undergoing beta oxidation, then it makes sense. It goes to there, but it provides you with a little bit of energy too, which is nice. So it's risen in popularity recently because the consistency of delivery over time. See here, it's the Vyvanse itself, breaks down relatively quickly, and then the amphetamine, it has a steady slope curve. There's not too much slope to it, and if you were to look at one of Adderall, it peaks up around 2 or 3 and then just plummets down at 4. So it's supposed to be not as much of a crash, so to say. Abuse potential, I mean, it's still an amphetamine, but like in reference to other amphetamines and stimulants, it has low abuse potential because you cannot do you can't manipulate it and do different routes of administration to get a more euphoric effect. It has to be ingested. It has to be taken up through the GI tract. Otherwise, it's just not going to be as effective. Well, I guess you could inject it, but that would be a dangerous game. That and then due to it's because there's not a peak and a crash, it has slower potential to be abused. And then the enantiomerically pure aspect is what makes it a really big selling point, is that they're essentially marketing it as a more pure form of Adderall with less side effects. Okay, alternatives. Sorry, I put them upside down, but I'll start with methylphenidate. So methylphenidate's been around since the 40s, started being used consistently in the 50s as a treatment. And you've probably heard of it as Ritalin or Concerta. It has the same function to increase the concentration of synaptic monoamines, but it has a very high abuse potential. And yeah, so has a high abuse potential, and it's been declining in recent years in reference to the popularity of other stimulants being prescribed. Then you have standard amphetamine salts, and that's the majority of ADHD prescriptions. So they're 1 to 3 ratio in weight. So for however many milligrams